Okay, so let's also use differentials to help us evaluate, or I guess I should say estimate error. And I have this propagated error highlighted here as opposed to relative error. And propagated error simply is, well, if you know something has an error in it that you, like maybe you know you are measuring something and you know it's accurate within a certain value. Just based on the accuracy of your instrument. But you use that measurement to measure something else. So you've just propagated that error. And so that, like what would that new, like what is that new error? If you compare that to what you should have got with like 100% accuracy, then we call that relative error. And if you multiply by 100, you get percentage error. So, so if I want to find propagated error when measuring volume here, right? I'm going to need to think about, well, what is the volume of a sphere, right? And so volume of a sphere is 4/3 pi r cubed. So I know volume is 4/3 pi r cubed. And so then normally I would just take derivatives. So I say, oh, okay, dv dr is equal to 4 pi r squared. But then I want to think about it with a differential. So I'm going to sort of isolate the dv part, and move the dr across. So dv is equal to 4 pi r squared times dr, the differential of r, and then calculate. So if I know my radius is accurate within a certain amount, how much impact would that deviate and impact the volume calculation? So it tells us within 0.1. And this idea of within means that I don't know if it's above or below. So it's going to be a plus or a minus 0.1. So that's going to be my dr. I'm going to hold on to that throughout the whole calculation, where my radius was measured to be 1.5. So plus or minus 0.1. So then plus or minus 0.1 times 4 could be plus or minus 0.4 pi times 1.5 squared, which is 2.25. And if I multiply that together, I should get plus or minus 0.9 pi. This is volume, so I should probably label it appropriately. So my propagated error, if I know that my initial measurement is within 0.1 as a linear measurement, and I'm using that for volume to figure out what is the volume going to be, it's going to be accurate within plus or minus 0.9 pi. So whatever the volume is at 1.5, above it or below it would be what this would kind of like give you in terms of that range. It's not the volume, it's the errors. How much are you within? And again, it's just an approximation with the differential. Okay. Now, if I want to know what is the relative error, so relative to what you should have gotten, so then we can say, okay, well, we take our deviation, right, our differential, and we compare it to what the real volume was. And I could do that. I could actually take this number and figure out what the volume was at 1.5 and do the quotient. But sometimes it's worth looking at, well, what did the formula look like, or what were the values of dv and v before you put in that particular point? So I know dv we said was 4 pi r squared dr. I know that volume is 4/3 pi r cubed. So there's some things that I can actually simplify before I actually do any numeric value calculation. Like the 4 pi's cancel. This 1/3 that was in the denominator, that can flip up to a 3 in the numerator. dr stays in the numerator, and r squared over r cubed could simplify to just r. So that might ease the calculation, especially if we don't have a calculator. So my dr was plus or minus 0.1. And my radius was 1.5. So then that's 3 divided by 1.5 is 2. 2 times plus or minus 0.1 would be plus or minus 0.2. And again, that's a relative error. If I multiply by 100, I get the percent error, which is not great. It's like a 20% error. But that's how you would calculate that. So watch out for the words propagated versus relative. Okay. So then, the next problem, the circumference of a circle is measured to be 56 centimeters, and it's accurate within plus or minus 0.1 centimeters. Okay. What is the propagated error in calculating the circle's area? So we want to be sort of careful, because circumference is a linear measurement, area is a quadratic or a squared measurement, and it's and I want to go through my circumferences formula and get to area based on the fact that they both involve the radius. So my thought here is, let's first start with circumference and look at that. So circumference is 2 pi r. Do the differential. So the amount that c will deviate will be equal to basically the derivative, so 2 pi times dr. And this dc was that plus or minus 1.2 equals 2 pi, and then dr, that's what I'm looking for. So divide the 2 pi across. So that's my amount that the radius would deviate. So then go back to area, which we said, or we know is pi r squared. Do this differential, so dA is equal to 2 pi r times the differential of r, or the amount r deviates. And so then this is what we're looking for. We know this, and kind of interestingly enough, we technically know that as well. So even though I'm not going to solve for the radius explicitly, although I could, because if I know circumference, I can find the radius, that given value of 56 pi for a circumference is actually, oh, sorry, not 56 pi. Just 56. That given value is actually what this 2 pi r represents, that this idea of, right, it's 56. So I can sub in that 56 right there, because this does represent circumference. So it's kind of a nice little, as my son would say, a hack, if you will. So we can substitute that in. It doesn't always work, but in this case it does, which is nice. So equals 56 times the plus or minus 1.2 over 2 pi. Okay, and so then whatever that value is equal to, I suppose we go to the calculator, since this is, not the nicest or cleanest of numbers. So we could have, let's see, 56 times 1.2, and then divided by 2 pi. Make sure you use that as a quantity, 2 pi, there it is. So we get 10.695, and don't forget it should be a plus or a minus. 10.695. And probably should use, centimeters squared. So that would be my propagated error for area. Again, it's not the actual area, it's how much I would deviate. So about 10 above or below square centimeters. Okay, then part B says, okay, well, what if we have a goal of 3% accuracy? Let's use differentials to help us evaluate this question. So circumference, if computing the circle's area, cannot exceed 3%. So let's start there. Let's start at the circle's area. And this kind of goes back to like, okay, so relative error would have been the ratio of our propagated error compared to the actual area. And if it says 3%, that would have meant that my relative error would have been multiplied by 100 to get that value. So that means that this ratio, if it's a 3% error, within that 3%, its a relative ratio would be 0.03. And just from the other problem, the differential of area we knew was 2 pi r times, I want to say dr dt, but it's not a rate, just the differential of r, and area itself was pi r squared. And so from that, I have a lot of things canceling. Pi r cancels, one of the r's in this pi r cancels, so I get this plus or minus 0.3 is equal to, it looks like I have just a 2 dr over r. And in fact, I can divide out this 2 over here, so 0.03 divided by 2 would be, okay. So plus or minus 0.015 equals dr over r. And even though I haven't really calculated anything, I'm kind of done. Because if you look at the problem, it says, what is the maximum allowable error in measuring the circle's circumference if computing the circle's area cannot exceed 3%? Oh, well, I'm close. Very close. Okay, so going back to this. So this dr over r, well, that represents the relative error in measuring the radius. And if you go back and you think about, okay, circumference, we said was, circumference was 2 pi r, and then if I do the differential of c equals 2 pi times the differential of r, notice that they both are linear measurements. So that if I wanted to know what the circumference would be, compare that to c. So compare that to the actual circumference, which is 2 pi r. Notice what's happening. The 2 pi's cancel, 2 pi's cancel, and that the relative error for circumference is actually equal to the relative error for for your radius. So that means this dr over r is exactly what I was looking for. And so that's plus or minus 0.015. That's relative error. If you want to convert it back, you could say it's times 100, so a 1.5% error. So plus or minus 1.5. So that means you have to be accurate within 1.5% of measuring to guarantee you have a 3% error or less in finding out the area. Okay?